let's go. Recall. The Sunshine Theorem, that's right. So what were we doing? We're talking about total variation. So TF, total variation of a function f. So this is the supremum over all partitions. We have some interval a to b that f is on of, so each partition is t0 less than tn, which is the other endpoint b, and the supremum is to take f at tj, subtract the value at tj minus 1 in absolute value, and sum as j goes from 1 to n, and then take the supremum over all the partitions. Right? And f is of bounded variation if tf is finite, when f is the graph of a curve for f equals gamma, tf is the length, and bounded variation is rectifiable. Okay, just some notational stuff. We proved that TF, the total variation, is the positive plus the negative variations. And we proved that f of x can be recovered as, well, you start with f of a, which you can stick someplace, and then add on the positive variation from a to x, and then subtract off the negative variation from a to x. And in this way, f is the difference of two increasing bounded functions.
Wait, are we taking the convention that NF is negative?
Negative variation.
Does that say NFAX?
NF from a to x.
NF
Yes.
The
NF is positive.
I mean, right, because TF has like the absolute value.
Has the absolute value.
Right,
So the
exactly.
NF is whenever this interval is negative, you put a minus sign, and whenever it's positive, you put 0.
Exactly.
Okay, so this is positive variation. This is negative variation. And we proved the theorem that f has bounded variation if and only if f is the difference of two increasing bounded functions. Increasing bounded functions. Okay? And then we did the rising sun lemma. Rising sun lemma due to Riesz, which I will now spell correctly. I before E, especially in Riesz. So let, again, G is a continuous function. Continuous. And let's make the rising sun set. Let G be continuous. Let E be the set of x from A to B such that there exists some positive h with G of x plus h strictly larger than G of x.
Yeah, it's open.
Then E is open. E is, as an open set, it's a disjoint union of intervals, countable. And G of AI is equal to G of VI, except for the last endpoint, at which case you have that inequality, meaning the first endpoint.
Can you look down a little bit?
Down?
Thanks.
Okay, so G is any continuous function. E is this rising sun picture. Again, whatever G does, if this is G, then you have these kind of hills. Well, in this case, it's the whole thing, so I haven't drawn it that well. Let's say this is a little higher. So then there's this kind of interval and then this interval. So these are the intervals of E.
Where the sun doesn't reach.
Sorry? Where the rising sun is shady. Yeah. Yeah.
Wait,
Where the
so
sun don't shine.
We have equality except at the very last index.
Yes.
Okay.
Very.
So it's equals except maybe at AI equals A. But in fact, all I will really want in a minute is the less than or equals sign. Okay, how are we going to use this lemma? We're going to use it a lot. We're going to use this lemma a lot. And we're going to use it when we start studying differentiation.
Are we past the mistakes in the book? Like, that was it?
Was that it for the mistakes in the book? Well, I don't know. There might be more mistakes that we'll come up against. But for now, yes, that's all the mistakes. In fact, the book does have a corollary which treats this issue and the making it open issue. But anyway, it's a good book.
So
It's a good book.
were your issues pedagogical or were they related to like actual egregious errors?
So I think the book takes the set E not to be in A to B, but in minus infinity,
Oh,
so that you don't stop at A.
oh, I see.
That might be one way that, in fact, they might be okay.
And then how do they define g of x for x less than a?
Right. Right.
Just extend, I guess. Just
They don't say, they just say the set of X without specifying where. So you have to interpret it the right way. Anyway, we all know what the lemma is trying to say. Okay, so what we are trying to, so our goal is that if f has bounded variation, then then f prime exists. F prime exists almost everywhere. Okay, so let's look at this condition, f prime exists. So again, if it's bounded variation, it's a difference of two increasing functions, so we may as well work with an increasing function. So let f be increasing.
And by f prime, we mean the limit as, the usual definition.
Yep.
Okay.
And we're about to get into the gory details of exactly that.
Okay.
So let f be increasing and define what are called the Dini derivatives. It's an Italian mathematician. Dini derivatives. It's amazing this thing has a name because it's like the most obvious thing you would think of, but somebody had to think it. So we'll call them D plus F. There's going to be 4 of them. This is the lim sup as h goes to 0 from the right of f of x plus h minus f of x over h.
h goes to 0 plus means h decreases to
Decreases to 0. Okay, so in other words, h is bigger than 0 and goes to 0. Then there's d plus f. Which is lim inf.
No, there's gonna be
Or
two
lower
other
minuses are
minuses.
coming. There's gonna be 2 other minuses.
And a d minus f,
You could do a lowercase d.
which is a lim sup as h goes to 0 from the right.
Why can't they pair them? Like,
And a d minus, which is a lim inf as h goes to 0. Sorry, I screwed this up. It's supposed to be pluses mean you're coming from the right.
Bottom top means.
Bottom top means lim sup lim inf.
Okay.
It's logical. Okay?
But it's always dividing by h, even if h is negative.
That's right.
Okay.
Same as the derivative, right? If h is negative, you still divide by h.
Except in the multivariable derivative, you divide by norm of h.
Because you can't divide by
Because you can't
a
divide by
vector.
It's weird.
Yeah. So that's why we're doing real real valued function. Okay, so obvious things, d plus is bounded by, d plus lim inf is bounded by lim sup in both cases, whether you're approaching from above or from below. And so we have several things to prove in order to establish. So what does it mean that the derivative exists? It means all of these things are equal. Okay? We don't want like a one-sided derivative. We want all these things to be equal. So f is increasing. Let's say it's increasing and bounded. And we're going to add the extra condition. I wrote the word bounded. I added the word bounded there. I'll rewrite it here. So we know what the Dini derivatives are. So f is increasing, bounded, and let's add the word continuous at a first pass. Okay, we're going to be working with continuous functions for a while, and then we'll see what to do with jump discontinuities. So if f is increasing, the first thing we want to know, so step one, is that the upper positive derivative is finite almost everywhere. So the claim is that the upper
So is lim sup from the positive side?
lim sup from the right, coming down to 0, is finite almost everywhere. This thing is finite almost everywhere. Okay? All right, let's prove this. Proof. Okay. Good. So the first thing we have to do, which is an exercise in your homework, is that this function df plus actually is measurable. Okay, that's not immediately obvious, but it's an exercise for your next homework. Not hard. What this means is that for all, let's say, n, if I let En be defined as the set of x in the interval for which d plus f of x exceeds n, that's measurable. Okay? And the set, so what I'm trying to say is that the set of x for which d plus f is equal to infinity, that's the intersection of all these ENs. So I want to get a handle on the measure of the ENs and show that those measures are going to 0 so that this thing has measure 0. Okay? Here's what we're going to do. So apply, here's the trick. There's going to be a bunch of tricks like this in this approach. Apply this rising sun lemma to g of x equal to f of x minus nx. Remember what this tells you. There's a set, which we call E, which is the set of x in the interval, such that there exists an h positive, so that g of x plus h is greater than g of x. Right? That was this rising sun set. But what does that mean? Let's put in what g is. This is f of x plus h minus n times x plus h is greater than f of x minus nx. I'm just putting in what g is on both sides. I have an nx here and an nx here. They cancel.
fx plus h minus fx greater than b.
Yes, greater than n. So this means f of x plus h, I'll bring this x to the other side, is greater than nh.
And in this case, our h is positive, so we can divide without changing the sign.
Okay? So, what does this mean? If there exists an h so that this thing is greater than n, well, that set certainly contains the set where the sup is greater than n. Okay? So this set E contains En. Contains En. Now this set E is open. So E is open, so it is the union, disjoint union of a bunch of intervals. Disjoint union of a bunch of intervals, AI, BI. And on those intervals we have G of AI is at most G of BI. And let's work out what that means. What that means is, remember what G was, f of x minus nx. This is f of AI minus NAI is less than G of f of BI minus NBI. And let's rearrange that. That says that f of BI minus f of AI is a lower bound for n BI minus AI.
An upper bound, right?
Is upper bound. This is the implies symbol. That this thing is an upper bound for this. Okay.
Can you explain why G is increasing?
In the rising Sun Lemma, G is not increasing because G can go up and down.
Yes, but in here you said E is a disjoint union of AI and BI, and also we have.
This was the conclusion of the rising Sun Lemma.
Oh.
This set
Oh.
E decomposes into
Oh, yeah.
is an open set, so it has some intervals, and on those intervals you usually have equality except for the first endpoint, but I don't even care about that. Let's just put the inequality.
No.
So this is a very clever packaging. It's a good way of packaging the sets where things could go wrong in this Dini derivative getting large.
So this G is saying when is f growing at least as fast as n?
Yes.
It's-
When is the derivative
Yeah.
at least n? That's literally, yeah. Or where is there at least one place where not the instantaneous derivative, but a global derivative grows at least like n? Because that'll be where is an instantaneous derivative also. Okay, so now we're almost done. So, the measure of En is measurable. It's contained inside this set E, the rising sun set, which itself is a sum over these AIs. And the measure of all those AIs is BI minus AI. The BI minus AI individually are bounded above by 1 over n, a sum over I, f of BI minus f of AI. But f is increasing. So the most it can gain from AI to BI, and then to the next AI to the next BI, is the amount that it gains from beginning to end.
You could just say that's less than infinity.
I don't want to do infinity. I want to do. I want to say
The bounding.
the endpoints.
Yeah. So I have a question.
Please.
We took a moment to say f is bounded, but if it's just a function that's on an interval, then it's automatically bounded because it takes real values.
Yeah, I mean, unless it's infinity for a set of positive measure. It's an extended function.
Okay. So you want it to not take infinity on a set of positive?
That's right. And because I want it to be increasing, I don't want it to take infinity ever.
Like
Once it takes
the
infinity,
last, at
What
B,
is-
it could be.
Right, what if it gets stuck at infinity, but then, yeah, once it hits infinity, what if it
Okay,
just
from
gets
down.
stuck? Does that still work, or,
I don't want functions that are infinite for
cause then you have to
a positive.
subtract infinity with infinity?
Yeah, I don't want to do that. Yeah, we just have a regular old. By bounded, I mean not on the extended reals, but just on
So
the
it's
reals.
just
It's just a real valued function from a closed set A to B. Okay, nothing funny. It's not going off. I mean, because B is closed.
Yeah.
I don't want it blowing up. Okay, so we have this increasing function. So we use the fact that f is increasing to go from this step to this step. This is all the like incremental increases over the intervals, but that's no more than the total increase that the function gets because it's increasing. And so let's go back to what we were trying to. So that implies. Come on. What's going on?
Wait, is B necessarily in,
No, the tip. I had a good tip and it got worn off. So is B necessarily?
like, is little b necessarily in this set, in this disjoint union?
No. All I'm saying is you have a function. So no, I just have a bunch of endpoints. Let's draw a
But then,
picture.
you know the inequality is true for the endpoints of this disjoint union, but like, and you know that A,
Whatever. Oops. Whatever f is doing, it's increasing on A to B. So it gains some amount. It gains some amount here. And it gains some amount here. And it gains some amount here.
oh wait, we assume that
I'm
F
assuming
was
that big F is
increasing, right, because we said bounded variation might as well work with increasing, yeah.
So we may as well restrict to increasing function.
Yeah.
So f is increasing. Okay, so f is increasing. I don't know what it's doing.
Yeah,
But on each interval, I have some amount that I gained.
yeah.
And I add all those intervals up. Those are all subintervals of A to B. I couldn't have gained more than what I gained from beginning to end.
Yeah.
Okay? So the set of x where this upper derivative is infinite has measure that's less than 1 over n times this finite thing. And that's true for every n. And there's no n on the left side. That's why I wanted a uniform bound that doesn't depend on. I get a different decomposition for each n here. But they're all no worse than the total growth of the function. Question?
So you are using some kind of Borel-Cantelli lemma to find the measure of lim sup of set.
It's less than, I'm not taking, well, it is the intersection. It's the intersection of a bunch of things whose measures I can bound by.
But the sum is not bounded because of okay.
Yeah, I'm not saying something about the series converging. Yeah.
Wait, so when we say bounded, do we mean bounded in the function bounded sense or bounded variation?
No, bounded.
Okay,
Yeah,
so
just
not-
increasing, it's increasing. I mean, it's equivalent because for an increasing function, its variation is just how much it increased. Because there's no variation, it's just,
Okay.
yeah, for any partition, what the amount of gain that it gets from A to B is f of B minus f of A,
Okay.
anyway. Okay? All right. So, so that was step one. Step one was that this, so this implies, come on,
It's running out.
I should have brought the other one. This was doing so well. All right, everything's falling apart. That implies that this D plus F is finite almost everywhere. Okay, that's what we wanted to establish. The next thing I want to establish, so step 2, is the claim that in fact D plus F is at most D minus F almost everywhere. So as I approach, so the lim sup from the right is bounded, F is increasing, it's bounded by, from above by the lim inf from below. And I claim that finishes the whole argument. So step 2, so proof that step 2 implies theorem. Well, we have D plus F is at most D minus F. That's what this claim will tell us. D minus F is at most D minus F above, because the lim inf is at most the lim sup. Now here's a trick. If this is true for every increasing function, apply step 2 to f of negative x with a minus sign. So let me slide this up a little bit. What happens? Here's my f of x. It's increasing. So negative f of x is just, I flip it over the y-axis. That's negative f. And negative f of negative x is I flip it over the x-axis. If I flip it over the x-axis,
Is x driven by the origin?
I'm trying to, if I flip it over the x-axis, here we go. This thing.
Yes.
Okay? The point is that's again increasing. And its lim inf from the right is the lim sup from the left. So the fact that d plus is at most d minus for any f applied to this function tells you that d minus from above is at most d plus from below. It switches lim sups and lim infs, switches the inequality, and switches which way is from the right and from the left. I'll leave that as an exercise, if that was a little fast. So think about this. So this is apply step 2, and you get that. And that, of course, is bounded above by d plus f. And that means and that happens almost everywhere.
So that would imply all of them are finite.
So f prime exists almost everywhere.
Oh my
And all of them are finite. Exactly.
That's crazy.
So all of them are finite at n equal. Okay? So all I have to show is that d plus f is less than or equal to d minus f almost everywhere.
What about D lower plus F? We have, oh, it's in there.
It's in there because of exactly this. This argument is
I
to
think
go-
I misread earlier. Yep, I see.
And the lower plus is bounded by the upper plus, always. And the upper plus is finite, so they're all equal and they're all finite. Almost everywhere. Okay, so it remains to prove step 2. So proof of step 2. All right, let's look at the set where it's not true. So the set of x for which d plus f is strictly greater than d minus f is the union of sets of the form d plus f is at least greater than or equal to. Let's take, I want to be careful, let's not be careful. Greater than r, and d minus f is less than. So if there's space between them, then there's some space between them. So then this one is bigger than r, and this one is less than r, and r are two rationals, and big R is the bigger one. Okay? So we're going to look at so if this thing, so I want to know that all of these have measure 0.
So why did we use two
So,
I want to separate. So if there is some distance between these two, then there are two rationals, one of which is an upper bound for this one of which is a lower bound for that one, with r greater than r.
I'll just wait for the rest of the proof.
Well, oh, you're saying just use the same one. Now, it'll actually be convenient to have daylight between them as well. I want space between everybody.
and then you choose rational, so this is a countable.
This is a countable union.
Yeah.
Make this countable, so if each of these has measure 0, so want this to have measure 0 for every r,
Right.
for every big R and
But if
little
it
r.
were just an uncountable union, then you wouldn't be able to say anything.
I wouldn't be able to conclude from this having measure 0 that this has measure 0.
Yeah.
The fact that I can take it countable.
So how do we count the number of these sets? We use bigger R or smaller?
Well, there's infinitely many sets. There's infinitely many sets, but if all of them have measure 0, and they're countably many sets of things measure 0, give you a set of measure 0. I want this to have measure 0. Because I want the reverse inequality almost everywhere. Okay. So let's look at one of these. Let's give it a name. What should I call this? ERR. So this thing is E big R little r. Okay, let's assume by contradiction. I tried pretty hard to make this not a proof by contradiction, but it's just so much more convenient to do it by contradiction. And you'll see we're really using the contradiction. So assume that the measure of that is indeed positive. Okay, it's measurable. It's definitely measurable. These are two measurable sets. It's measurable. So there exists an open set which contains ERR and is contained inside A to B. Let's not make it too big. I want to still be able to measure E on it. It contains E with, what does it mean to be measurable and to have positive measure? So there's a set that contains E, but its measure is not much bigger than E, with the measure of O bounded by the measure of ERR times some room. And the room is big R over little r, which is a constant greater than 1. So Charlie, that's one place where I'm using the fact that it's one of several places that are about to happen where I'm going to have this separation from both sides.
So instead of additive room, you gave it multiplicative room.
Which is equivalent only if this is strictly positive. That's why I really need to assume the contradiction.
These signs could be messed up. R over R could be positive over negative.
No, the derivatives are all positive, are all non-negative because f is increasing.
But we've just taken the union over all R and R and Q.
But now we took little r greater than 0.
So
Greater than or equal to.
that's a comma, that's in the union. Okay,
Yeah.
okay.
So it's R greater than R greater than 0.
Greater than 0. Yeah. The derivatives, f is increasing. So none of the Dini derivative things are going to be negative. Okay? So again, we have this set ERR. Assume by contradiction it has positive measure. What we'll do is we'll bootstrap it to have too much measure, more measure than itself. So first of all, it's measurable. That means we can find an open set which covers it, whose measure can be bounded by the measure of E itself times a multiplicative factor greater than 1. Because we can do this plus an epsilon, but we can turn that epsilon, given the size of this being positive, we can turn that epsilon into some constant multiple. Okay, that's the first step. Now, being an open set, this, come on, you gotta last me another 40 minutes, buddy. This is a disjoint union of open intervals. Intervals IN. Okay? On each interval, we're going to apply, on each IN, apply rising sun. First we're going to apply it to g of x equals, actually, I'm going to apply this on, well, you'll see in a second, negative f of negative x plus little rx. Let's apply this to negative the interval. So whatever this interval was, I'm going to just flip it. And on the negative, because that's where negative x lives. And I want to apply it to this continuous function, negative f of negative x plus r. And let's see what it says. So what is the rising sun set? It's the set of x in negative IN, for which there exists a positive h. Remember, rising sun is about positive h with g of x plus h greater than g of x. Let's unpack what that is. Let me slide this up. Let's unpack what that is. That says negative f of negative x minus h, because it's x plus h in parentheses, plus rx plus rh, plus rx plus h, is greater than negative f of negative x plus rx. The rx's cancel. I'll move, so now let me change, that's what this thing was, so let me change the condition. The condition will be x is in IN, so I'll replace x by negative x, once I get rid of these. I can replace x by negative x.
So you're saying these two are the same set?
They're not the same set, but the conclusion that I have about this set, so this set is, that set flipped over the x-axis. The conclusion about this set is that on this set, this set is a disjoint union of open intervals. This is open. Then this thing is open. Well, then this thing is also open. I'll move this to the other side, and and let's look at what this says. So there exists an h positive. Move that to the other side. This says that f of x minus h is positive, so I'm approaching x from below, minus f of x. I've moved this to the other side, so now I have a less than sign, r h.
And this is identical, right? Because you're only evaluating f, like switching the IN to minus IN.
I lost you.
Who thought of this?
You'll see. No.
This is what I'm thinking. I'm just like, how long did this take someone to think of?
Well, because anytime you make a g, which is an f plus rx, and you look at what this says, it says that the derivative is doing something.
Well, that's fine, but I'm just saying this
And when you're
whole approach, it's just very.
These are clever people.
Yeah, clever
Reeds.
people.
Wait.
Sorry, Andre was in the middle of
Yeah,
it.
so, I was just not, why doesn't the sign for h flip as well?
Well, we can make it flip. So let's make the sign for h flip.
Okay.
Okay? So at the moment, all I said is, look at this condition. That's what this condition is.
Okay.
And now everywhere we see x in this condition, we can replace it, we can flip the whole thing. This was x in negative I. Let's flip everything so that x is in positive I.
And then that's equivalent to what you wrote, the conclusion.
The conclusion is that this set is open. That's all I'm concluding. And at the endpoints, I have inequality.
Were we saying that those two sets were equal? No. X and minus I and X.
They are, one is the flip over the x-axis of the other, over the y-axis of the other.
Negative reflection.
Just a negative reflection. Okay? The only conclusion is that it's open. That's all I'm trying to say. Okay? And now you want to make this a plus instead of a minus, so let's say there exists an H negative.
Okay. Wait, don't you have to then add a sign to the bottom, or?
You're right.
Or flip the inequality.
Or the, reflect the inequality.
I have to flip the inequality. Hang on 1 second. Is that right? Yes, I think I do want to flip the inequality. No. Yes.
This is too smart.
This is a little too bunny out of a magic hat thing.
I'm scared.
No, that is the inequality that I want.
I'm in danger.
That is the inequality that I want. So let's just think about this for a second. If there exists a positive, let's go back to H being positive for a second. Let's go back to H being positive. And this is a minus sign. This is still measuring the Dini derivative. This is still measuring the Dini
If
derivative
you're going
from
H
below.
positive, it's from below. Oh, wait.
The directions are off, right?
The
Yeah, it's
directions
like
are off.
The top is from below and the bottom is from above.
Yeah, I need to flip it. I definitely need to flip both. If I'm flipping this, I need to flip both. So, if H is negative,
Is it when you change from minus IN to IN that the entire X plus H changes to minus X?
no, because this was a condition on X.
Okay.
I put in what G was. I made too many changes at once, right? That's what you guys are confused about. I should have done this in like six iterations of.
I just feel like that would have taken too long.
That, well, it's taking even longer. If I confuse you, it takes much longer than if I just write it out and everyone's on board. Let's do it again. Okay. What is this condition? This condition is, let's put what G was. Can you still see what G is? Yes. So it's negative f of negative x plus h plus r x plus h is greater than negative f of negative x plus rx. Okay? That's all that said. So,
Sorry. Long night.
okay? So that's this condition that x is in negative in. All right, let's massage this. I'm moving this to the other side. We can kill this rx from both sides. I'm moving this to the other side. F of negative x minus h minus f of negative x is bounded above by RH. And h is positive, so when I divide by h, there's no problem. Great. That's all. Let's leave that as that. Okay? So what we said is the set of x in negative in, so that this happens, so that there exists a positive h, so that this happens, is open. Is open, so it's the disjoint union of some aj, bj, and g of aj is at most g of bj.
So you're scrapping going through the.
Let me do it much slower instead of trying to do it all at once. Let's follow through what that means. What is g of aj? G of aj is, can you still see where f was? Right there at the top. So it's negative f of negative x plus rx. Negative f of negative x plus rx. No, I really don't want the negative I in there. Well, okay, you'll see in a second. How do I want to say this? I really do want to flip it. Well, these are, I want to say, these are intervals, but they're the wrong intervals. I want to look at negative this.
So you flip it, it inverts the inequality?
Yes. So negative this set is a disjoint union of things. or this set is disjoint union, but I'm going to call them, they're going the wrong way. Colin, I still lost you.
No, sorry, I'm just very tired.
Okay, here's the original set. Okay, let's draw a picture. Here's the original set E, R, R. It's contained inside an open set, and that open set is a bunch of intervals. So let's look at one of those intervals, IN, that contains the ENs, ERRs in them. Okay?
Which may not be contained in ERR. It overlaps with
It can overlap, yeah. Doesn't have to, it's a cover. The INs cover ERR, because the open set covers ERR. I take that IN and I flip it over the x-axis. So here's negative IN.
Just the endpoints flipped.
The endpoint's flipped, okay? I applied the sunrise lemma, and I got a bunch of intervals that break up INN. I want to flip those intervals back. That's what gives me these AIJ. So these are my AJ, BJ. It's when I flip back that I want to have these AJ, BJ.
So what did we call the sunrise set for G?
The sunrise set for G, we didn't give a name. We just wrote it. This is it. This is the sunrise set for G.
So
Because I applied G to negative IN.
But then would it have to be G of AJ greater or equal to, yeah, okay.
Once I flip it, the role reverses.
Yeah.
G was smaller here, so it's bigger here. And similarly here, I have this inequality, but now it's not negative. So G was on the negatives.
Yeah.
So when I flip, now I get a positive. What I don't want is this negative sign in there.
Wait, but wasn't the negative already in front of the side?
G is acting here, and now I want to see what that means about F back here. So when I move,
I mean in front of that, the bracket, the top bracket.
let me do this. A typical subinterval of this set will be negative BJ, negative AJ.
Sure.
And so this says negative BJ is bounded above by negative AJ.
Sure.
Now let's plug that in. That says at BJ, that's bounded above. This is at BJ, that's an AJ. So I have negative F of negative negative BJ plus R times negative BJ, so minus R BJ, is bounded above by the same thing with AJs.
Because in the definition of G, there was already a negative. Is it like F of negative X?
Yes, this
That's what
is,
cancels that out.
yes.
Okay.
Wait, so without the minus from the set, we have, it's a union of, disjoint union of AJ, BJ, so then when you apply the minus again, you get a union of minus BJ minus AJ?
Yeah.
So let me call this disjoint union negative BJs to negative AJs.
Okay.
So that when I put the minus sign, now it goes AJs to BJs.
Okay.
Now, this applies to negative BJs to negative AJs. So that's the inequality I get for G. What does that inequality tell me? It tells me that negative F of BJ minus R BJ, because that's what G is less than or equal to negative F of AJ minus little r AJ. It's about to get worse. We're only halfway there. We're going to use this trick again.
Halfway.
We're going to do this again.
We didn't even do this for non-continuous functions yet.
That'll be a different argument. That'll be a different argument. That's not as bad. Well, it has its own pitfalls. This is tricky, so I don't mind going slow. This is tricky. What have we concluded? Let's summarize, okay? So the interval IN, well, let me fix this a little bit, and then we'll summarize. So let me move this to the other side. I have F of BJ minus F of AJ is bounded below by R AJ minus BJ it's not what I want. I want it the other way around.
Was that the right sign for G?
What you said is correct as part of it, on my copy.
Yeah, but it's not correct as far as what's in my notes or what I want. Sorry, I'm at the second step. We're gonna go backwards. This implies. Let's just follow it through and hopefully it'll work out in the end. Haha. Yeah, here I'm getting R AJ minus BJ. Damn it. This is a positive number. So saying that it's bounded below by a negative number is useless. We need to get this inequality right. Is this really
Well, how was G defined again?
G of X?
But AJ minus BJ is positive, right? Because negative AJ was the left bound and negative BJ was the right bound.
Right, so what I want to say here is R BJ minus AJ.
No, that one is negative, the way
No.
you defined it. Because
R is positive and BJ is bigger than AJ.
well, you said this interval is minus BJ minus AJ? So absolute.
Yeah.
So when I flip it, I get AJ to BJ.
Yeah.
And that's where I want to apply G. Yeah, when I... This is very frustrating.
Because you had a negative in front of the bracket above there already, so I don't know if you needed the negative with the G.
Well, G, let's write what G is again. It's negative f of negative x plus Rx.
Yeah,
Sorry?
like you added the negative, like if you pull the page down, the top one, there was a negative in front of there.
There.
Yes. So, like, maybe you overcompensated for the negative.
No, there's definitely just a sign floating around that's ruining everything. You're ruining everything, sign. And I want this inequality the other way around. I want this to be, and, no, yeah. I want this. Okay,
Wait.
I want to know that f of AJ minus f of BJ is bounded above by R times BJ minus AJ.
That's what you
do-
have.
then you do
You
have
have that. I computed
Because-
that from assuming
Yeah, because
G
when
of
you
minus
move it
BJ is
around
less than
and you
G of
multiply by
minus AJ.
-1, then that's what you get.
But when I multiply by -1, don't these flip also?
No.
Oh no,
you have
thank you. Thank you. I move this to the other side, I move that to the other side, I multiply by -1, and that's what I have.
Yeah.
You guys are happy, I'm happy.
I'm
Good,
happy.
good. Okay. That's what we have on these AJs and BJs, and by the way, these AJs and BJs were on IN, and there's one for every, or there's countably many for every IN. So this is really AJ, BJ, so this is
Oh, yeah.
on IN.
How could you explain again? I
Wait,
mean,
uh,
if you
I'm
go
not getting
again,
this.
right?
No,
No,
think it works.
it doesn't work.
Someone said something out loud that isn't what's
Yeah,
written
no, it
down.
didn't work.
It doesn't.
It doesn't work, right?
If you want to hold.
All right.
What was said out loud works,
Could be
but
R,
what
AJ
was-
minus
You have
BJ.
f of AJ minus f of BJ.
It should be
Yes,
AJ
it
minus
should be R,
Right.
AJ minus BJ.
Yeah.
That's scary.
No, but that will be negative. No, I definitely want this.
Floating around.
I definitely want this. Because look, what are we trying to say? This is the set, let's go back to what this is supposed to be. This is supposed to be, where's our U? Where's our E? ERR. I'm trying to get this condition in terms of increasing sets. Sets on which something's happening, right? I want to capture this condition, and that's the condition that the lim inf from below is at most R. What does it mean that the lim inf from below is at most R? It means that this difference is at most R. And I want to do that interval by interval. I want to take like large intervals where this happens. You follow? No.
Well, I get the philosophy,
But not the proof.
yeah.
All right. Let's get this right. Let's try again.
Can we
This-
change the definition of dx to f of negative x plus I? The definition of dx.
You wanna change like the second sign?
No, the first side.
The first term?
You change it to f of negative a plus I.
Oh yeah, like getting rid of the first negative.
Just getting rid of
Would that do it?
I mean, that's still an even number of sign changes.
No, but I don't care about f being, will that do it? Will that do it? That's gonna flip these guys. Yes, I think that might do it. That's not what I have. That's not what I have. But I think that might do it. Because that's the issue we were having back here, right? It's not the right condition. H being positive. Look, the Dini derivative, right? Let's go back to the Dini derivative. Let's go back to all the way back here. What happens when H is negative? When H is negative, we're dividing by a negative number. So that ratio, but of course that is a smaller, if f is increasing, we have to divide by a negative number because we're saying, look at a previous value and subtract away the current value. That's a negative number. You have to divide by a negative number so that the ratio is positive. The derivatives are always non-negative. Okay, so that should be a negative number. And look at what we're dividing by here, or rather,
There you're dividing by a positive number.
now I'm dividing by a positive number, and this is an earlier value, so this isn't right. This isn't right. I do want a negative f, and I think if I just replace f by negative f, I get to put a minus h there, and then I get exactly what I want.
Yeah, and you're saying that this is an earlier value because we're in minus in, but then the negative h doesn't change, right? So.
Right, so this is at negative x.
Okay, yeah. Yeah, that is the signs don't match up in that.
The signs don't
portion.
match up there. So let's apply it. Okay, let's try this again. I do want to get this right, and I want you to understand it. So let's try. I like the suggestion. Can I just change it on here, or should I do it all over again? Do it all over again. You guys will be happier if I do it all over again. Okay, start over. Start over. Try g of x is equal to f of negative x plus rx. All I want to do is get the rising sun lemma going the other way. Forget about the negative x. Let's do f of x plus rx, but now it's the setting sun instead of the rising sun. Okay? Let's do the setting sun lemma. All of this is happening is because I want to apply it to a different lemma, and I don't want to state that lemma, and I'm trying to be slick. Let's not be slick. Okay? What's the setting sun lemma? Let's go away. Go away. We have a setting sun lemma, which is, here's our function again, but now the sun is over here, it's setting. And so I want to know if I have a function g on AB, and I look at the set of E, which is x for which there exists an h negative, such that g of x plus h, which is now before, wherever this x was, I want to know, so here's an x, and I want to know, can I look back and find a larger value? Can I look back and find a larger value? And if I can, then I call that set E. Then E is open. E is a disjoint union of a bunch of intervals, AI, BI. And what happens on these intervals? Well, except for possibly this endpoint B, that maybe this is what happens. Maybe the endpoint B, G of AI is equal to G of BI, except at the endpoint it might be that it's BI is the smaller one. Let's not do this flipping around thing. Let's just state the setting sun lemma. Are you okay with the proof of the setting sun lemma? It's the same picture, but now the sun's over here.
Yeah.
Okay? So now apply the setting sun lemma. Apply, I like this better than setting sun, to g of x is equal to f of x plus rx.
Setting sunset.
Restricted to in. setting sunset. Yeah. That's right, instead of the rising sunset. Okay, so what is the setting sunset? It's a set of x so that there exists a negative h. Good, we're on our way to d minus. For which g of x plus h is greater than, there's a future value where it's greater. I mean, there's a value in the past where it's greater. That is what I want, I think. We're going to see in a second if that's what I want or not.
Those are x.
Okay, so these are gone. I subtract that. Yes! I divide by a negative number, and that flips the sign. Okay, that's all we were trying to do. That's all we were trying to do.
Yeah.
Okay? So if this thing is bounded by R, then the lim-inf, if the lim-inf is bounded by R, then there is some small from below, then there is some h from below that's bounded by R.
So you get the top is negative and the bottom is negative too, right?
Both of these are negative.
Yeah.
So that this being bigger than being bounded by R is an actual restriction. Great, that's a better way of doing this.
But what is the minus signs? If you know.
It's that h is negative. So when I bring RH to the other side, I bring f of x to the other side, I get a minus. I bring
Yes, we have a minus, and if we minus some h, which h is smaller than 0.
That's easy to fix. That's easy to fix. Then I bring it over here, then I divide by h and there's a minus.
Okay, I'll think about this.
Please don't find anything, please don't find anything.
No, now I'm very confident.
Negative.
I mean, I was happy before, but just the explanation of how you do the flip is very confusing. This is a much better
This
presentation.
definitely works. Yeah.
This works, this works.
Okay.
Are we sure?
And so we have these, so this set is equal to this disjoint union of AI, BI. No question about whether that's in negative I or something. And G of AJ is at least G of BJ. Because that's what that setting sun.
So I don't know if this is a problem, but this set seems empty, right?
Why?
So f of x plus h for negative h is to the left of f of x.
Yes?
And we're saying that when we subtract r times h, which is the same, is that a positive or a negative number? For a moment ago, it felt like that
The
we were
top
going to
is
get
negative.
some
Here?
condition that's impossible. The line above.
The line above.
Yeah.
So I had a minus Rx, minus Rh, and a minus Rx. The two minus Rx's I just canceled.
Yeah.
I moved the f of x to the other side. I moved the minus Rh to the other side to get a plus Rh, but h is negative.
Oh, I mean, just stay on that line.
Yes?
H is negative.
H is negative.
Minus RH is therefore positive.
That's right.
And so we're saying that f
But this is negative too.
H is negative.
H is negative.
Yeah, so
So if you look at a previous value of f, and you add some positive amount,
Okay.
you exceed the value, the new value of f.
I apologize.
No worries. No, let's get this right. Okay? So now let's parse what this says. This says, this should now be correct. F of AJ minus R.
No.
Maybe this will be okay. Let's see.
No.
No, it is okay.
Okay.
Whew.
Thank God. This is like a suspense movie.
Yeah,
So let's read
this
this.
works, this works.
The f of bj, I'll move the f of aj to the other side, is bounded above, which is exactly what I want, by r times bj minus aj. Okay. Let's do it again.
Oh, no.
So that has gotten, you see, the first step was just to get us an open set, to get us these intervals, In. On these intervals, we can study what's going on. And now we looked at the condition. This is going to contain the condition that D minus is less than R. Now, on each of these AJ, BJs, we apply the rising sun. Apply rising sun to G of x equal the usual f of x minus Rx. Minus is the right thing here.
Minus big R now.
Big R now, because we're going to catch the other condition.
Mm.
So this is restricted to AJ, BJ. Then the set of x for which there exists a positive h, so that G of x plus h
Now there's a future value.
a future value of G is greater than G of x. That is open. It's a disjoint union. God, what do I call these things? How about
AJ prime.
AJK, BJK?
If we're doing double subscripts, the previous one should have been
Yes,
JN.
J, yeah, maybe with a superscript N everywhere that we're not keeping around.
Because it depended
Okay.
on IN.
It depended on IN. There's one for each IN. Okay, so if you want to keep the N's around, so we have triple scripts, sub and super. So this is the set I'm interested in, and look at what it says. It says f of x plus h minus f of x. These guys cancel, is greater than R h. H is positive, so I bring it here. Perfect. And G of A, J, K, let me not put the N's, it's already bad enough, is less than or equal to G of B, J, K.
Yeah. Expand that out.
And let's expand that out. This is f of A, J, K minus R times A, J, K is less than or equal to f of, B, J, K minus R, B, J, K. And let me move this to the other side, that to the other side. That tells me that f of B, J, K minus f of A, J, K is bounded from below by R times B, J, K minus A, J, K. Okay. Now we are in position to study all of these. So let ON be the union of over all J and K of A, J, K, B, J, K. And this is a disjoint union because for different J's they came from different subintervals and they were all disjoint. Okay? This is an open set in IN. And notice that E, R, R intersect IN is contained in here. Precisely by construction. It's the set where the lim sup exceeds R, and the lim inf from above, and lim inf from below is at most little r.
Doing ERR intersect I.
Yes, I want ERR intersect IN is contained in
What
O.
was ERR again?
ERR, all the way back at the beginning,
Is the set where things went wrong?
is the set where things went wrong. We want to prove that D plus F is less than or equal to D minus F. So let's look at the set where that's false.
Yeah.
That is the union over R and big R and little r,
Yeah.
of where this one's bigger than big R and this one's less than little r.
One specific one is the ERR.
one specific one is an ERR.
Okay.
I want to show that all of these have measure 0.
Yeah.
Okay? So we've taken one of these. We took one ERR. First, we contained it in an open set, which we broke into INs, disjoint INs. On each IN, we caught that condition on subintervals AJK. And on each AJK, we caught that condition with AJBJ. And then on each AJBJ, we caught this condition with AJK, BJKs.
Yeah. Okay.
So that's what these things are. And they catch both conditions because they were subsets of subsets that caught that condition and then caught that condition.
Yeah.
Okay?
Mm-hmm.
Let's compute the the measure of this thing. Let's do this right. So the measure of ON, which of course is an upper bound for the measure of this. Well, what is that? This is just the sum over J and K of BJK minus AJK. BJK minus AJK is upper bounded. This is an equal sign. This is an upper bound by FBJ minus FAJK divided by R. Each of those, so for a fixed J, each of these sums is at worst, for a fixed J, each of these sums is at worst f of Bj minus f of Aj.
He's just taking the,
Because those bits add up, are all contained inside AjBj.
and we have an increasing function, so.
Yes.
Yeah. Okay.
Okay? Now, on AjBj, we had a reverse inequality. What page is this? On AjBj, we had a reverse inequality. Okay? So I'm going to stick that in, if I can.
So little r over big R?
Exactly.
Yeah. So back and forth.
And that whole thing is at most
B minus A.
b minus a, which is the measure of In. Okay? So what have we learned? What have we learned? So the measure of ERR, which is equal to the sum of the measures of ERR intersect IN, okay, because that's a cover. The INs make up a cover, a disjoint cover of ERR. That's each of these is contained in O. That's a sum of the measures of ON. What we just showed is that the measure of ON, this was on the other side, the measure of ON. The measure of ON is at most R over R times the measure of IN.
The sum, right?
The sum. The measure of IN adds up to O, and all the way back 100 years ago, we had an O.
We had a condition on O.
We had a condition on O, 6, 5.
Is the R over R lower than?
Yes, the measure of O is strictly smaller. This was under the assumption that the measure of ERR is positive, was strictly smaller than this thing times big R over little r. So let's keep that. Let's keep that in sight. This is strictly less than R over R times the measure of ERR times R over R.
Oh my goodness.
And that is not possible. Contradiction.
How are you trying to do this without a contradiction? Just to wrap your head around it.
I mean, it's cute.
You see, what you want is this strict inequality. But you can't get the strict inequality unless you have room to get the strict inequality. And to get it, you need this thing to be positive. So if you can assume it's positive, then you get your strict inequalities. Then you do this massive rising sun, setting sun argument. And you just follow all of the pieces.
Follow all the pieces.
It's not nearly as hard as I've made it seem. There was a slick trick to try to just use the rising sun lemma twice instead of a rising and a setting. And that, I think, threw us way off course and confused us. But the argument itself, I think, is not that. Let's just look at it for. I'm not going to get to the next stuff in 2 minutes. Let's just look at what we did. Okay. Again, start with this ERR. Assume its measure is positive. Okay, it's measurable, so there exists some open set that contains it, whose measure is at most this. And the only reason I can do this strict inequality here, that's what kills everything, is because I'm assuming that this is positive.
Yeah.
If it has measure 0, then I can't get this
Factor
factor through anything. I need a plus epsilon, and that kills everything. Okay. This is open. On each of the intervals, we apply. So I want to apply rising sun to an interval. I don't know that this thing has any intervals in it, so I take an open cover. That has intervals. On each interval, so do not apply rising sun. So how much of this am I killing? All of it, I guess. Until I get to setting sun. Kill this page, setting sun.
Could you turn the last contradiction into something that just says the measure of that thing is less than or equal to 0? Somehow.
I can't get started until I get intervals. But where am I supposed to get intervals from if I don't have an open cup? You know, it's sort of begging the question to say, it's really useful to have the contradiction. All right, so we're going to try, we were almost there. This will be a minus Rx. On the setting sun lemma, so you apply the setting sun lemma to this. What you learn is that there are these intervals, Aij, Bij. Maybe it's better to keep track of a picture of what's going on. Here, let's keep track of the picture of what's going on. So we started off with some set, I don't know what it looks like, ERR. We covered it with an open. So we have these INs. On each interval, because it's an interval, we can apply, rising sun doesn't apply to some weird ERR set. We need an open set. On this thing, so we apply setting sun, because we need to get lim-infs from below. Lim-infs from below give us this setting sun set. On each one of these, we apply rising sun and get a further decomposition. And then you just follow the list of inequalities that each gives you. One gives you a less than R, the other one gives you a greater than little r and big R. They sound the same when I say them out loud, but they're different letters in my head and on paper. And then when you add all of this up, you realize that you've gained something and you couldn't have.
Yeah. And it's all disjoint because you're taking
And it's all
disjoint
disjoint.
unions and disjoint unions.
If I came to that conclusion, I would think I did something wrong.
Okay? So therefore, the derivative exists almost everywhere.
Yeah, because then you do that chain of inequalities that begins and ends the same.
Yes.
And everything pinched in between is the same.
Yes. And so all the limits exist from above and from below almost everywhere.